Hello, physics. We are starting chapter 17 here, electrical energy and current, and we will probably have a test over this chapter. And we're looking at section 1. Electricity is a challenging topic. It's not quite something that we can touch and feel like maybe balls in a projectile, but we can sometimes make analogies to what we are learning to some of the physical world. And one of the beginning spots here is electrical potential energy. Electricity can produce a force, which is a push or a pull. And so it can actually push or pull on atoms, other things. And so we can actually recycle this equation of mechanical energy that you might remember from before, where kinetic energy plus potential energy equaled mechanical energy. We even threw work in there. Well, now we're going to add another piece to this mechanical energy equation. We have kinetic energy plus potential energy gravitational plus potential energy elastic. That's like from rubber bands or things like that, springs. And we can add potential energy from electricity. So these things all go together. So if potential energy is one of the ingredients in this equation, in what unit will we measure potential energy of electricity in? And the answer is joules. All of those things are measured in joules. And so our electrical potential energy is equal to the charge, the magnitude of the charge, Q, and the electric field strength, how long that field is, and displacement. You can kind of think of it like work equals force times distance, which is also measured in joules, but that's a physical thing. This is electrical. Here is a diagram showing us field, electrical field. These arrows are showing which way the field is working. And this is a positive charge put in this field, and it will be moved along with the field direction, kind of like a ball in gravity. If you were to think of the ball in gravity, you could think of the ball being attracted to the earth, and we would just think about, well, what's the distance it's been lifted up, and up how far would it fall? That would be the potential energy. And it's kind of like that with electricity. That would be this distance is the potential energy that it can have. The one big difference between electrical and physical potential energy is that here a positive particle will be pulled this way in these field lines. A negative would go the opposite direction. In the physical world, we don't have some balls that go down and some balls that go up necessarily. But in electricity, we do. Depending on the charge, it can go one direction or the other. Just like in the physical world, if you move horizontally in the field, no work is done. Only if you move within the field lines. Then we talk about electrical potential. This is a little different than electrical potential energy. And this equation here is how much difference there could be. And it's voltage, which is kind of like how much push is there on a particular thing, and we use that potential energy electric, which was in our equation back here, divided by the amount of charge, and we can find out the potential difference. And that is, the unit for that is the volt, and it is equivalent to 1 joule per coulomb. And the symbol for coulomb is a capital C, as we saw earlier. And the unit for volt is the capital V. And notice this is a V as a symbol for a unit, not the symbol in equation. So this one is not italicized, whereas here it's italicized. And that is not the unit there. Talk about uniform electric field. Instead of not two little point charges working on each other, we can use this equation. You can follow the algebra there. And we get another equation for the potential difference. And it is the magnitude of electric field times the displacement. And lastly, we have another equation for potential difference or voltage is the Coulomb's constant times the point value of the charge times the distance between the charge and where it's going. At the bottom of our page here, we have the electrical potential at some point near a positive charge is positive, and the potential near a negative charge is negative. Here's an example in your book, and here's some notes on how to do some of the calculations, just some hints here, and a reminder of the charge from E that you can see back in the last chapter on doing our calculations. And that's it for section 1.